So this is the video series on exploration in DeepRL. In terms of exploration, that's our current agenda. So in the last week, we actually began with motivating the exploration problem, with defining the problem and introducing multi-armed bandits and the notion of regret to theoretically study exploration strategies. Then we actually introduced also exploration strategies that work well on small MDPs. So we used them to call them classic exploration strategies. We started with epsilon greedy. We then introduced upper confidence bounds and Bayesian upper confidence bounds. And we ended the session with Thompson sampling. In this video, we will actually talk about exploration in DeepRL. We will start with count-based exploration, then we do prediction-based exploration, and we will end with memory-based exploration. Okay, so let's get started with the key exploration problems that we actually have in DeepRL. And it seems that we can actually say it's two big problems that we care about if we care about exploration in DeepRL. The first one is actually the hard exploration problem. So the hard exploration problem actually stems from the fact that we actually have environments that have a very sparse or even deceptive reward system. And it is very hard to actually, from the provided rewards, it's actually very hard to get a running and well-performing policy out of it. The second part of the problem is that random exploration is often is very often prone to failure, and it will actually rarely find successful states or obtain any meaningful feedback from the environment. One of such examples is Montezuma's revenge, which we also had introduced in the last videos, but we will actually focus a little bit more in this kind of videos here. The second problem that we will also care about is the noisy TV problem. This kind of synthetic setup is actually proposed by a paper from Burda et al., where they actually formally define that problem where an agent actually seeks for novelty in the environment, and the authors actually place a TV on there, and the TV just switches between uncontrollable and unpredictable output. So you will just see images sliding through, and it's a random process that actually randomly select the images that are actually put on the TV. But you could also use something like Gaussian noise on it or something. And as the agent will always have a problem with predicting it, this will actually attract the agent's attention forever. And we will actually see that agents that are seeking for novelty and that actually maintain a prediction model, they will actually always actually get an intrinsic reward as it cannot predict the output of the image and actually the output of the TV, and it will fail actually to make any meaningful progress, and in the end becomes a couch potato, because you will actually see in such videos that the agents will just remain in front of the TV and just look at the TV, because they actually can never predict what's happening, and they actually mean that that they actually see something new. So it's actually here, it's a video of that proposed by the authors. So you have like a maze environment, and in the one environment you actually have the agent actually gets in front of a TV and sees the TV with the images, and it actually sticks to this position because actually it always sees some novel things in the environment, while if there is no TV actually present in the environment, the agent actually successfully solves the MDP. The second one is actually the problem of sticky actions. Actually, there's in the Atari setup, there's actually in these experiments, actually what we usually do is we actually have a noisy controller that repeats the last action instead of the current one that actually is provided by the agent. It actually repeats the actions with respect to some probability, and this is actually a setup that was proposed or suggested as a best practice for training agents on fully dynamic deterministic settings like Atari in order to prevent memorization. However, they also make the transition from room to room, except especially in Montezuma's revenge, very unpredictable in this case if we actually use this sticky actions flag, which we will actually need in deterministic environments. So these are actually two problems that we are actually mainly interested in exploration in DeepRL. And this is actually what we will be mainly focusing on in this video series. Okay, so the question now is, why do we actually need another lecture on DeepRL? The thing is, we actually studied the theoretical background when we actually talked about bandits in the last video. However, we cannot really transfer what we have learned in there. So because actually we had small MVPs, everything was actually there. We could actually calculate everything, and we cannot really like transfer something that we've seen in the bandit setting one-to-one on the DeepRL setting. So in the last video, what we actually covered was some kind of optimistic exploration. So we said that a new state is always a good state because we want to learn something about the environment. We said we want to estimate something like a state visitation frequency or the novelty of a state. And what we typically did is in the last lecture, we actually introduced an exploration bonus, which can be actually put on top of the reward that we actually provide to the agent. And in this kind of fashion, actually, the agent is incentivized to actually explore the environment and to seek novelty in the states. We can actually do this with the exploration bonuses, but we can also do the Thompson-style sampling algorithms, where we actually learn the distribution over Q functions, and then actually what we did is we sample and acted according to the sample. We did not really focus on information gain style algorithms and entropy loss and noise-based algorithms. If you're curious about this, you can actually look this up. There's like material provided in the references. However, we will be talking a little bit about information gain style algorithms in the second part of this lecture series. Okay, so the question now is, how can we transfer what we have learned in the last lecture to this lecture? And in order to do that, just maybe let's revisit what we introduced with the upper confidence bound. So in the upper confidence bounds, we actually said that the action that we select used according to our upper confidence bound is the argmax of our Q function, so the greedy action, plus some weighted with a hyperparameter, a weighted function, which we actually introduced as an exploration bonus. It's some function actually over n. We actually introduced also a few different exploration bonuses, so we can make of many different exploration bonuses. We do not really need to care about all the elements. The most important thing was actually that it needs to decrease with the number of with the number of visitations of an action. This is actually what we did last lecture. So now the question is, so we actually had a multi-arm bandit setup. The question is now, how can we actually make use of such methods in a full MDP? So so the idea is to say in the first setting is the first idea is to say we make a count-based exploration, meaning that now instead of just counting actions in a multi-arm bandit setup, just count the number of state action visitations, so actually how often we selected a certain action in a given state, or we select the state visitation frequency, and we then add an exploration bonus based on this number. So instead of counting the number of arms in the bandit, we now count the number of times we actually visited a state or a state action pair. So that's the basic idea that we will also follow along in order to actually transfer what we've learned in the last videos to the DeepRL setting. And then if we follow this, actually we instead of providing a reward to the agent, which is actually R as of A, we just provide a new reward function, which is actually composed of the reward we actually get from the environment plus some bonus function over our visitation counter that we actually have. So this would be the counter, could also be n of SA in this case. And if we formulate our exploration strategy, our exploration bonus strategy like this, we can give it actually to any model-free agent, because actually we just need to override, so we can actually switch this between the environment and the agent. We can just implement this at this line, and we can actually use any model-free agent that we have actually seen so far within the lecture. We can also make this a little bit more general. So a general formulation would look like something like this. So the reward that we actually provided sometimes time step t is actually composed of the extrinsic reward, which is actually what we are getting from the environment at time step t, plus some hyperparameter times the intrinsic reward at rt, where actually which is actually here's beta. We say here the beta is a hyperparameter that adjusts the balance between exploitation and exploration. However, it means exploitation of the of the extrinsic reward over the intrinsic reward. So in other words, our I of t, so the intrinsic reward, is nothing else than the exploration bonus that we actually had at time t. Yeah, so the intrinsic reward is actually an idea that is inspired from intrinsic motivation that you can also find in studies from psychology, and actually we can transfer those findings to RL2. So we want to actually incentivize the discovery of novel states, and we want to improve the agent's knowledge about the environment. So this is actually studied a lot in psychology and neuroscience, and this is also what we want to introduce in RL. So you will actually find a lot of somehow connections to such communities when we talk about exploration and intrinsic behavior in RL agents. Okay, one another thing to this formulation. So while it is actually a good idea to just add an exploration bonus to our reward function, we really need to make sure that that we do not really confuse our RL agent. If we actually weigh the intrinsic rewards too large, because this actually means that when we travel along a trajectory, rewards will constantly be changing when we actually visit the states. So this is actually something that we need to take care of, so that we actually do not get confused with this. Other than that, it's a really it's a very reasonable idea to do it, and we can actually take it as a hyperparameter that we also optimize through our through our grid search that we need to do anyway. Okay. Okay. Sorry. This is okay. This actually needs to decrease with the number of visitations. Okay, so this is it as an introduction to the exploration problem in DeepRL. So now let's actually talk about how can we do a count-based exploration in DeepRL settings where we actually cannot really count so much. So the general idea in count-based exploration is that we actually need to count states, and what we actually want to do is we want actually novel states. Because actually novel states surprise the agent. So actually what we need is we need a metric that measures how novel a state or a state action pair appears to us. And the intuitive idea that we also followed a little bit in the last lecture was that we count how many times we actually saw a particular state, and we then apply the bonus accordingly. So in other words, we let n at n of s be an empirical count of visits of a state s in a sequence s1 to n. So this is actually what we can actually use as a metric. However, the problem is also that we have seen, like in lecture 405, that if we have a high dimensional or even continuous state space, we will actually have two problems. So many states we will actually never see at all. So for instance, this is the example of Multisuma's revenge, which could be something like a high-dimensional state space because we have a pixel image. If we see this exact image here, for instance, for 10 times, the count would then be 10. However, what if actually you see the same image again, but the agent looks in the other direction? So actually it's not really a difference. So in fact, it's not totally different. However, the count is 0. And the problem is that if we have such a high-dimensional state space, you get combinatorially many states, and the chances of actually visiting the same state again will be really like close to 0. And also remember that by definition of some math, we actually forced some visitation counters to be 1, and this could actually be a little problematic in practice. Another thing is actually that we also see many states actually never again. So if we have a continuous state space in here, we never, the state space of this hand and the grabbing example, it's a continuous state space, and we will actually never see a state twice. So the chances of seeing a state twice is actually closely becoming 0. So in both examples, we have many zeros in our state visitations, but we somehow need. So this actually this makes counting a little bit useless at this point. So counting will become useless. However, this is also a side note of what I just said. We need for most of the algorithms, we actually need a non-zero count for most of the states, even if we haven't seen them before, because then we divide by 0 and then most of the things will not work. However, at some point we need to exploit the fact that some states are more similar than others. And this might be something that is really useful to exploit. So in the example that I just said, where the agent just looks into the other direction, or in this state, the skull is here but a little bit to the left, actually the states are not that different. So actually those states are similar in a sense that from an exploration point of view, we could actually count them both as the same state. And this is actually something that we need to exploit if we talk about exploration. So the first thing that we can actually do is introduce by density models. So and actually what we actually want to do is we want to fit a density model P of S given a parameter, so it's a parametric density model parameterized by a parameter set theta, and we wanted this density model to actually approximate the frequency of the visits. If we have such a density model that actually provides the visitations, we can derive a pseudo count from that model. So in a sense, what can we do? At a certain time step, we have a true density at a time step t, which is nothing else than the number of times that we visited the state divided by the number of visits at all. And if we actually observe state S at time step t plus 1, then the true density of the density function should look like this. So it actually should increment the visitation of the states and also increment the number of totally visited state in these cases. So the question is, how can we get a density model P of S described by theta, and a density model that's actually updated by this, so we call this theta prime, to actually satisfy the above. And actually looks that we actually can do this. So this is a simple algorithm that's actually introduced by Belmar et al. In 2016, and the idea is the following. So first we fit a parametric model P, a density model, to all of the states D that we have seen so far. What we then do is we take a step T and observe a new state as T. And what we then do is we fit a new model PS or theta prime to the old data, and however we append the new state to the data set. So actually we have a new data set that's actually composed of the old data set plus the new state, and we actually fit a density model to that one. And what we then do is we use P of S given theta and P of S given theta prime to actually estimate the pseudo count in here. And then what we actually do is we set the entrance, we actually set the reward we provide to the agent as a sum of this should be the extrinsic reward in here, sorry, the extrinsic reward plus some bonus over the pseudo count, and then we start over again. Now the question is, how can we actually get this pseudo count? Because actually we do not get it from the density model as it is there. And so turns out that we can just do some linear algebra, because we actually have two equations and two unknowns. And from these two equations and two unknowns, we can reformulate them. You can do the math if you want at home, but you can trust me, this is correct. So you actually can reformulate those formulas, and you can put this one into that one, and this actually stems from the fact that you can actually calculate this pseudo count as a result of both density functions from the old and the new data set, and from this you can actually provide a pseudo count. And why is this actually working? So the idea is that that we actually use the density model to look at the counts, and the counts actually relate to the probability of counting them. So this is actually working. So we can actually use both of these theta parameters and density models, and actually combine them in order to get an estimate of actually how the pseudocode actually evolves from one step to another step. So each time step we can simply calculate head of ns, and then we can actually put this into this formula and we can run the algorithm. So now, having this framework of using density models, we have still two open issues that we actually need to solve. The first one is, what bonus function actually could we choose or should we choose? And the second issue, what density model could we and should we choose actually to be continuously training in our exploration strategy. So the first one is, we could simply use the upper confidence bounds that we actually introduced in the last lecture. So it's defined like this. It's a bonus over our state visitation or over our pseudo count. We can just plug it in and provide this one to as a bonus to our agent. We could also use MBIIB provided by Strehl and Lippmann, and which is actually a little simpler. However, as I said, the only fact is that you need something that actually decreases with a larger number of state visitations, or pseudocount in this case. And you can actually do something like this, where you actually also omit the sum. You can actually use something like this. Here you see the offset if the state visitation is 0. So the originally proposed paper, so the density model paper in here, actually uses this one, but however, you can actually use you can actually use any one of them. The second question is, what density model could we actually choose? I don't know if you're familiar with density models. However, we have a different optimization criteria as we usually use if we talk about density models like GANs or variational autoencoders. In this case, we need a model that actually only need rough densities. So we do not need a perfect accuracy or normalization, and we do not need a perfectly reconstructed images like we get in GANs. We also do not need to sample from the distribution. So actually in VAEs, and also in GANs, the really important aspect is also to sample from the distribution, which is something that we do not really need here. We only need to get, for the states, we need a function that actually gets up if the states have a higher density. This is the only thing that we need. And it turns out there is a bunch of density models that we can actually use. One is context switching trees, pixel CNNs, or Gaussian mixture models, for instance. However, there's much more, also stochastic neural networks. Context switching trees, for instance, is something that you can really work on images. So it takes a 2D image and it assigns a probability actually according to the product of location-dependent filters, actually. So, however, you look at the nearby pixels, and you relate this actually to the density of the of another image in this case. However, this model is very simple, and while it is simple, which is something that we always want, it's really limited in expressiveness and scalability and efficiency. Another thing is also Gaussian mixture models. So you can use a variation in a Gaussian mixture model to estimate the density of certain trajectories. And you can predict the probabilities actually to guide the prioritization of the experience replay. So this you can actually see in this paper, also very interesting to read. However, there's a bunch of versions that you can actually use in practice. So how is density models for count-based exploration actually working? So this is the results actually from the paper of Belmar et al. And what you see is, you see the average training score with and without using an exploration bonus, or with an optimistic initialization in 5 of the Atari games. So what you actually see in Montezuma's Revenge in here, you see actually you see something like the vanilla plain DQN, which actually doesn't solve anything in the environment. In some other environments, DQN works better actually in Freeway and Venture and Hero. It really gets something. However, what you see actually is that the density base, which is the green one in here, it actually it actually gets a decent reward in Montezuma's Revenge in here, and then also in the other games, it really does a good job. However, there's also cases where actually optimistic and DQNs together are like on par with the density models estimation, where there's actually no real add up to the reward that the agent achieves. However, it also doesn't get worse, so you can just put it on top on any algorithm, like switching around optimistic exploration, which is something like epsilon greedy, and put this into the DQN, and then can actually work with this. This is also a nice visualization of sorry for this one. So this is actually a nice visualization of how you can visualize the exploration. What you see is the number of visited room in a hierarchical tree-based structure, which is actually the known world of a DQN agent. And you see that if you use a bonus, you will actually find a lot of more rooms if you introduce the count-based exploration bonuses. So in here you have no exploration bonus, and by chance the agent will find another room. However, this is like nothing that you really can guarantee for. And in here you see like that the agent is like really finding a lot of rooms using this exploration bonus. Another idea to actually use count-based exploration on like high-dimensional and continuous state spaces is not using density models, but to use hash functions. The question is, or the idea is, what if we still count the states, but we count them in a different space? So the idea would be the following. We map a high-dimensional state space into a k-bit hash code via an encoder function that actually is a parametric model or something else, like a hash function, over the state, and then we count actually the hashes instead of the raw observations. What we usually want to do is we want to make this hash code smaller, of course, than the original state, which means that we usually have a lossy hash function, and this is actually what we call the encoder. I think this is intuitively correct. So if we use shorter codes, we will actually probably have more hash collisions. If we have similar states, we might have similar hashes or not. So actually this is something that we need maybe to look into it a little bit more. So if we have similar states and similar hashes, the question is also if we have hash collisions. So if we have shorter codes, we have more hash collisions. And the question is this good or bad? So I would say it's not bad if similar hashes get similar codes. However, what if similar codes do not get similar hashes? So this would be something catastrophic, because we actually saw a new state that's actually already got is falsely attributed to state that I visited often again, and we will not get a reward for finding a new code. So this is something we really should be aware of, and this would be a bad idea. So there's an algorithm called locality sensitive hashing, and the authors of this paper actually they propose a hashing scheme that preserves the distances, so the distancing information between the data points in the hash. So close vectors in the raw observation state actually obtain similar hashes in the encoded version, so in the hash, and distant vectors actually also have different hashes. They also propose an algorithm called SimHash, which actually uses something like an angular distance to measure the similarity of two states, and there you can have some math. So you actually have a matrix A that you actually we actually draw each sample from a normal distribution, and then you will actually map this onto an angular distance that you are actually optimizing. And in this case, actually, if you use larger Ks, you will get a higher granularity and fewer hash collisions. You can also put this in a little algorithm. So like for each of in iterations, you just collect the state action samples, you compute their hash codes, and actually also update the hash table, because actually you now need to maintain a table of the hash codes and actually to count, and then you can actually update your policy using your rewards and the bonuses that you actually draw from the hash table. The authors also propose the learning of hash codes actually. So this was some SimHash was actually some version that has a static hash table that's actually learned. However, we can also work on high-dimensional state spaces. So SimHash actually, they found actually that SimHash works poorly on high-dimensional images that also have a complex structure. Because actually the similarity is actually calculated on a pixel level, and this actually fails to capture any semantic similarity. And the idea is now to learn the compression of, which is very similar to a hash. So learn the compression of the image using an autoencoder. And the idea or the intuition behind that is that the hash collisions are actually fine if they do not cost much in their reconstruction. So usually when you train an autoencoder, you map a high-dimensional image through a bottleneck, which is usually something much, much smaller, and you want to actually reconstruct the image well. And the intuition is that if you have hash collisions in the bottleneck, they are fine if the reconstruction is not really like taking it badly on you. So actually, if the reconstruction error is not really affected by the bottleneck representation of the image, it is fine. So this means that similar images, we get also similar hashes, and then we get the hash collisions in the end. And so learning hash collisions will actually cause them to be similarity driven. So there's a special dense layer they use, and they use k-sigmoid functions in the latent space to actually generate a binary activation map in here. And this is the loss function for this one. So you just train the autoencoder, but you have some, I would say, regularization term on there. So this is the usual reconstruction loss. So you actually want to have the input to be equal to the output. And here you have a sigmoid activation function in the bottleneck, and you actually want them to be close to binary, so that you get a hash code in the bottleneck. And this actually forces to be that the hash code in the middle, so the activations are equal for images that have for different images that get less reconstruction error. So actually you get similar hashes for similar images because actually the reconstruction error will not that be high. Okay, so this was it with count-based exploration. In the next video we will talk about prediction-based exploration.